Hey everybody, welcome to day 2 of our flipped classroom. I'm really excited today to talk to you guys about formulas and phases. So yesterday we spent a while talking about how do we symbolize things, right? We talked a little bit about using the particle diagrams, which that's going to continue today. But we're also going to talk about a few other ways to symbolize different elements, compounds, mixtures, and we're going to talk a little bit about the phases of matter. So let's go ahead and dive right in. So your worksheet today, or your notes sheet if you're following along, starts with a couple of Regents questions. Now, I'm going to introduce you to these questions slowly, at least at the beginning of the year, but these are the style questions that you can expect to see on the Regents exam if the Regents exam happens in June. So let's go ahead and take a look. First question says, which particle diagram represents a sample of matter that cannot be broken down by chemical means? So key words here, right, is that they cannot be broken down by chemical means. So that means that even if we undergo a chemical reaction, it will not break that substance down, which must means that it's already in the simplest form of matter, which therefore would make it an element, okay? And so which particle diagram represents an element? Letter D. All right, question number 2 here. And again, feel free to pause the video if you want to try the questions on your own first. So question 2 says, given the 4 particle models, which 2 models can be classified as elements? So remember, things that are considered elements are going to have the same type or identical types of atoms all the way throughout the sample. So if they have more than one type of atom, it cannot be an element, okay? So question number 2, let's take a look. So number 1 contains 3 types of atoms that cannot be an element. Model 2 contains only 1 type of element, so that is an element, or I'm sorry, 1 type of atom, therefore it is an element. Number 3 does contain only 1 type of atom again, so that will be an element. And then model 4 contains 2 types, and therefore that's not an element. Therefore, answer choice 2 and 3, or letter C, is the correct answer. All right, diving right in. So again, we used particle diagrams yesterday to talk about elements, compounds, or mixtures. Again, let's just do a quick review here with these elements, compounds, and mixtures. So particle diagram number 1 that we have right here, notice that we have 2 identical atoms. They are combined to form a molecule, okay? But if we have 2 identical types of elements, that must mean 2 identical types of atoms, that means it is an element. Okay, taking a look at particle diagram number 2 here, notice that we have this molecule repeating, and within that molecule we have 2 types of atoms. Therefore, in particle diagram number 2 here, this has to be a compound. Okay, and then in particle diagram 3, notice that again, we have only 1 type of repeating atom. Therefore, for particle diagram number 3, if we have only 1 type of atom present, it is going to be an element. Okay? Now, taking a look at these particle diagrams, one thing that I do want you to notice that is different than what we've previously looked at is now we're starting to see some molecules that, for example, in number 1 are really spread out, okay? And we have some particles in number 2 that are closer together. And then in diagram number 3, we have some particles that are really compact. And so what we're going to continue on to talk about at this point is how can we symbolize solids, liquids, and gases, and how can we describe them? So we're going to pop over to the descriptions first, and then we'll continue on with the particle diagrams and kind of going back and looking at them and determining them as elements, compounds, or mixtures. So let's go ahead and first talk a little bit about solids, okay? So solids, and again, this is something you should have previously covered, but solids, okay, are typically going to be tightly packed, okay? They are going to have a fixed volume, okay? And they are also going to have a fixed shape, So a definite shape and definite volume, that's another way to word that. And they are typically very organized. If we think about how they move, it's weird to think of solids as moving, but solids are actually constantly moving. And we typically describe that movement as vibrations. So we say that they vibrate. Fantastic. Let's go ahead now and talk all about liquids. Okay. So liquids are usually going to have a little bit of flow ability. We like to describe the movement as flow. And so instead of being tightly packed, we like to say that they are loose, okay, but still touching. Okay, and in terms of a volume, if I take a glass of water and I pour it into a different glass, that volume does not change. Therefore, we still have what's called a fixed volume. However, if I take my glass of water and I pour it from one glass into another or one container into the next, what can change is the shape. Okay, so we say that it has no fixed shape or an indefinite shape. Okay, and then we like to say that again, we said that we like to use the word flow for the movement. All right, let's talk about our last state of matter. Okay, and that is the gas. Okay, now gases are spread very far apart. Okay, so they're spread out, and we usually say that they take the shape of the container. What does that mean? Well, for example, if I were to take a sample of gas out of a balloon, let's say I had a helium balloon in this classroom, and I were to release the helium from that balloon, the helium would spread out into every single corner of my classroom until it fills the space that it can occupy. And therefore, we like to say that it has no fixed volume, okay, and no fixed shape. And it usually takes the shape of its container. Okay, oops, so no fixed volume, and then we're just going to erase that, and we're going to say no fixed shape. Okay, and then in terms of movement, gas particles are really cool because they move very, very quickly. Okay, so they move very fast. So flipping back to our particle diagrams then, which of these is which? So again, we have our particle diagram number 1. This looks spread out. The particles are not touching, and therefore this would be our gas. Okay, in particle diagram number 2, we have particles that are a little bit closer together, but not organized, and therefore these are our liquid. And then for particle diagram number 3, it's compact and organized, and therefore this represents a solid. Okay, fantastic. Now, in terms of these different particle diagrams, I may or may not ask you at some point, hey, why don't you draw me a particle diagram of, let's say, bromine at room temperature? So the question then is, well, how do I know what temperature bromine boils at? How do I know what temperature bromine is going to melt at? Okay, and that's information that we need in order to understand how to draw that particle diagram. So I'm going to attach to today's lesson the Regents Chemistry reference table. And I want you all at this point to maybe just pause the video, and I want you guys to kind of open up that reference table. And I'd like you guys to take a look at reference table S. Okay? And reference table S, you'll notice, has a lot of information, but it has the boiling point and the melting point of different substances. Now, bromine is element 37. Okay? And bromine actually is going to melt at 266 Kelvin. And it's going to boil, okay, at 298 Kelvin. I'm sorry, at 332. So 332 Kelvin. Okay, and I want to know at 298 Kelvin, what would happen to that bromine? Okay, what phase would that be in? So we have our melting point, we have our boiling point, and I want to know at 298, what phase would we be in? So looking at these, how do I determine that? Well, if the substance has already melted, it would already have gone from that transition of a solid to a liquid. Okay, so we have to look at 266. Has bromine melted if it's already at 298? And the answer is yes, okay? So it's already past its melting point, which means it's already transitioned from solid to liquid. Well, what about boiling point? The boiling point is 332. And again, this would be when it transitions from liquid to gas. And so it has not yet transitioned from liquid to gas, and therefore at 298, bromine is a liquid. So what would that look like in terms of a particle diagram? One thing to remember is that bromine is diatomic, so it is Br2. So in terms of a particle diagram, we might want those two atoms, two Br atoms, to be combined together, but remember they have to be identical. So I want you to go ahead and practice drawing what that would look like as a liquid, so feel free to pause the video if you'd like. Okay, and I'm gonna go ahead and sketch that out right here. So again, we have our liquid, so we want our particles to have some space and not really be organized in any specific way. And we want there to be, I usually say for liquids to keep them towards the bottom of the container, okay? That way there's no confusing them for gases at all. All right, awesome work. So now I want you guys to notice on your worksheet, if you are following along, that I've given you a variety of different symbols here. Now, symbols are used a lot in chemistry, as I've already mentioned. So we have Hg with an L here. We have He with a G. Okay, we have Na as an S, and we have the O2 as an AQ. Okay, and I want to point out that symbols here are used to represent the phase of matter. So if I have an L, that's going to represent a liquid phase of matter. If I have a G, that's going to represent the gaseous phase of matter. If I have an S, then that's going to represent the solid phase of matter. And if I have an AQ, this one is special. This represents the aqueous phase of matter. So let's go ahead and define what it means to be aqueous. If we look at the base of the word aqueous, okay, if we look at the base of the word aqueous, you'll notice that you might hear the word aqua, right? Like aqua, which usually means water. So an aqueous substance, okay, means that it is a solution, okay, or a mixture, okay, in which the substance is dissolved in water. Okay, so aqueous means it has been dissolved in water. So that means that if we see aqueous, we know that there's two things present. There's the substance that we're representing, so in this case, oxygen, and we have aqueous, which means it's also been dissolved into water. All right, next thing I want to go ahead and cover is I want to talk a little bit about the idea of the elements versus compounds and how we represent those using the letters or the element symbols. So we have three here. We have CO, CO2, and C little o. Now, I want to point out here that these all contain the same letters, but they're very different. Our first one is carbon monoxide. Okay, we have carbon dioxide. And then we have the element cobalt. Okay, and what I want to point out here is notice how carbon monoxide and carbon dioxide both contain two capital letters. If there are more than one capital letter present, then that means that there is two elements present. Each capital letter represents a new element. Therefore, over here with cobalt, we only have one capital and a lowercase, and that means that this is an element, while both of these are compounds. All right, everybody, the video is going to cut short here. In class, I do want to go over the last portion of the guided worksheet, so we'll go ahead and do that together tomorrow. Have a great day, everybody.